welcome to this today's lecture. We will continue the same topic that we started in the last lecture, and this lecture is on the some standard probability distribution on continuous random variable. So, in the last class we covered some of them, and in this class also we will cover some of them. And as I mentioned in the last lecture, that all this theory, all this description, all these properties of this standard distribution will be used while we are taking some modeling approaches for some civil engineering problems in the subsequent modules. And also I mentioned in the last lecture that whatever the distribution that we are discussing, those are mainly focused to the problems related to the civil engineering. Maybe the list may not be complete, but these are the distribution which are used in the civil engineering. So, in today's lecture, when we are talking the same topic on this probability distribution of continuous random variable, this is continuing from the last lecture, and in this lecture we will cover these distributions. The beta distribution will start, then gamma distribution, Pearson distribution. Basically this Pearson distribution is a family of distribution, and there are many such families. For this Pearson is one of them, and in this family there are 7 different types of distribution. And in civil engineering, particularly in the hydrology and water resource specialization, this is important for the analysis of this hydrological analysis, that is known as this Pearson type 3. So, this Pearson type 3 distribution will be covered from this family, and also some cases where it is known as this log Pearson type 3 distribution. And after that we will discuss about the general extreme value distribution. Again, in this extreme value distribution family, there are 3 different types, depending on their some of these parameter properties, and most useful in the sense, in this context of this civil engineering problem, this Gumbel distribution, which is the extreme value type 1, and the extreme value type 3 distribution is known as this reverse Weibull distribution, and we will also cover the general Weibull distribution as well. So, maybe this line what is written, that extreme value type 3, this extreme value type 3 is related to the reverse Weibull distribution, and reverse Weibull distribution, and this Weibull distribution also will be covered in this lecture. There are some more distributions. Before I proceed to this main part of today's lecture, which I should mention that there are some more distribution which also will be covered. For example, that chi-square distribution, T distribution, F distribution, and these distribution are mostly important not only in civil engineering, in all different problems where we need to test some statistical data. So, for those kind of statistical test and the hypothesis testing, which will be mostly covered in the last module of this course, and in those applications, those distributions are also important, and those distributions also will be covered either in this module or in the last module. So, we will see that. Basically, today's lecture we are starting with the those distribution which is not covered in the previous lecture. So, we will start with the beta distribution. This beta distribution basically is a general case of the uniform distribution. There is a similarity between this beta distribution and the uniform distribution, in the sense that both this distribution is having their specific bound. So, both that lower bound and upper bound. We have seen that, for example, there are some distribution which are not bounded in the sense that the support is the entire real axis. For example, the normal distribution, which is whose support is from the minus infinity to plus infinity. Then we have discussed in the last lecture that the exponential distribution, that exponential distribution we have seen that it can take the positive values. So, it is the lower bound is at 0. So, that distribution here in this lecture we will see the gamma distribution, that gamma distribution is also having the lower bound at 0. Similarly, some other distributions. Now, the uniform distribution that we saw in the last lecture, that it is having both the bounds, the lower bound as well as the upper bound. Similarly, that beta distribution is also another distribution for which that lower bound as well as the upper bound exist. So, this beta distribution is a 2 parameter, which is alpha and beta, 2 parameter continuous distribution, and the distribution is defined over the interval 0 to 1. So, this interval, when we are defining this beta distribution on the interval 0 to 1, this is known as standard beta distribution. This is similar to that, similar in the sense that we also use the same terminology for this normal distribution to this standard normal distribution in the last lecture. Similarly, here this, when this beta distribution is defined over the interval from 0 to 1, it is known as this beta, that is known as standard beta distribution. Generally, in general case, the beta distribution can also be defined over an interval having both the lower and upper bounds in the general form like a and b respectively. If the limits a and b of the beta distributions are unknown in some cases, then it becomes a 4 parameter distribution. So, this alpha and beta are the two parameters, as well as these bounds are also becomes 2 more parameters. So, that will become a 4 parameter beta distribution. Now, this beta distribution, if the random value takes on the values between this 0 and 1, its probability density function is described by this beta distribution, which is given by this form, that f(x), the density function is x power alpha minus 1 multiplied by 1 minus x power beta minus 1 divided by a function which is known as the beta function, and this beta function is having the parameters alpha and beta. Note here that the range that we are that the support of this random variable is from 0 to 1, and both these parameters alpha and beta are greater than 0. Now, this beta function that we are talking is an integral form of like this, x power alpha minus 1 multiplied by 1 minus x power beta minus 1 dx. So, this integral form is known as this beta function with parameter this alpha and beta. This can be shown that this can be related to the other functions like this other function which is known as gamma function. So, this is related to this gamma alpha multiplied by gamma beta divided by gamma alpha plus beta. Now, this gamma function again is the another integral form which is shown here, this gamma with a single parameter alpha, which is the integration from 0 to infinity x power alpha minus 1 e power minus x dx. Now, this gamma function also will be used when we discuss this gamma distribution, and there are some very specific properties are there that we can utilize. For the time being, as we have shown that this alpha is greater than 0. So, for some specific values this gamma function is known. So, it can be shown in such a way that this integration, if we know this value from this 0 to 1 range, then the value of this gamma function can be calculated based on the simple properties, and those properties we will discuss in details when we are talking about this gamma distribution. So, with this, so this gives the complete distribution, that is complete density function for the beta over the support 0 to 1. Now, if we calculate this cumulative beta distribution function, which you know from the previous lectures, that this is the integration from the left support, that is from the 0 in this case to some particular value x, that is the cumulative probability. So, this will come to this form which is this beta x alpha beta. This is defined by this integration form, that is 0 to x x power alpha minus 1 1 minus x power beta minus 1. This is from the same principle of this cumulative distribution, and it is normalized by the same beta function, where this beta is explained earlier, that is 0 to 1 x power alpha minus 1 1 minus x power beta minus 1 dx. Now, we will just see that how this beta distribution is related to the uniform distribution, or in other words, how we can say that this uniform distribution is a special case of this beta distribution, and this distribution we generally apply where both the upper limit and the lower limit are known for a random variable. In that case, this distribution can be used, and depending on these parameters, this is that alpha and beta, we will see in a minute that how just controlling this parameter, how the shape and location of the distribution can be controlled, that we will see now. So, here you can see we have plotted three different PDF, that is probability density function of the beta distribution. We are just varying its parameter. Now, if you first see this blue line, this is the parameter, the first thing that before we come to this one, the first thing that we see, that you see its support of this x is starting from 0 and going up to 1. Now, this for this blue one, if you see that this alpha is equals to 2 and beta is equals to 5, some value has been taken like this. And now, if we take the value alpha equals to 1 and beta equals to 1, then you see that this is becoming flat. So, which is nothing but the uniform distribution over the range 0 to 1. So, if for a beta distribution, if we set the parameter alpha equals to 1 and beta equals to 1, which is equivalent to the uniform distribution over the range 0 to 1. So, we can say that this uniform distribution is a special case of beta distribution. Now, if we keep both the parameters same, for example, alpha equals to 2 and beta equals to 2, then you can see that this distribution looks like this, which is a symmetric distribution and having its mean at 0.5, mean mode, obviously as it is symmetric. So, its mean mode and median coincides to this 0.5. It is not only for alpha equals to 2 and beta equals to 2. If you keep this parameter same, for example, alpha equals to 3 and beta equals to 3, then it will remain symmetric, keeping its mean mode and median at 0.5. Basically, it will change like this. So, its peak will increase. So, this is what is approximated there as this alpha equals to 1 and beta equals to alpha equals to 2 and beta equals to 2. Now, if we just increase this, that alpha equals to say 3 and beta equals to 3, then this will approximate look like this, it will be symmetric. And similarly, if we further increase these parameters, 4 beta equals to 4, and this again will, so its peak will increase, but it will remain the symmetric with respect to this mean will be at 0.5. Now, depending on now we discuss about the, if we change it, instead of just making it equal, if we just change it, if we see it on the slide again, that this one, that if we just change this alpha and beta are not equal, then how it comes. So, here the alpha equals to 2 and beta equals to 5, you can see here, and from our previous lectures discussion on this positively skewed and negatively skewed, you can see that this distribution is positively skewed, where this alpha equals to 2 and beta equals to 5. In fact, for any alpha which is less than beta, the distribution will be positively skewed, and it is opposite if we change this relation, that is, if we increase this alpha, when alpha becomes greater than beta, it will become the negatively skewed. So, what I am trying to say, the same plot, if I just take a different frame here. So, what is shown there is a positively skewed like this for this alpha equals to 2 and beta equals to 5. Now if we take this one, just reverse, there is alpha equals to 5 and beta equals to 2, the distribution approximately it will look like this, so which is a negatively skewed. So what we are trying to discuss is that this beta distribution having its specific bound from lower bound and upper bound, just controlling these two parameters we can give its different shape, different skewness, and it can even be the uniform distribution, just selecting the parameters are both are equal to 1. Now we will see its cumulative distribution for this beta distribution with those same parameter here. That is, first the blue one is showing you that alpha equals to 2 and this beta equals to 5, and green one is alpha equals to 1 and beta equals to 1. We have seen that in this case the distribution is uniform. So this green line is a straight line starting from 0 and ending up at 1. So this is the CDF for the uniform distribution. When alpha equals to 2 and beta equals to 2, we see that this is giving a nature that is cutting the point at exactly at 0.5 when this alpha and beta are same. Now if we increase this, both these values, alpha equals to, instead of 2 and 2, if we just give that alpha equals to 3, beta equals to 3 or even higher, so what will happen, this the slope of this one will increase. So if I just show it here, then what we will get is this one. So this is for your uniform distribution. This is starting from 0 to 1 and this is x axis is 0 to again 1. So this is your for the uniform distribution. Now if we increase this value from beta equals to 1, alpha equals to 1, this will looks like this. If we further increase this keeping this intersection point same, this will have more slope here, and similarly it will go on increasing with the increased value of this beta. Okay. Now when we are talking about this positively skewed and negatively skewed, how this distribution will look like is like this, that when it is becoming positively skewed, this intersection point will come towards this. So more if it is more positively skewed, then this can be even like this. So it will go to this higher probability quickly, which is the standard thing for this positively skewed. Now if it is negatively skewed, then what will happen, this will go, so this will take the lower probability first and then it will go and meet there. More negative, it will just show like this, it will go in this fashion. So just controlling the parameter, what we are trying to do is that we can cover the cover a wide range on this paper. So just depending on this how these parameters are selected. So this is a very important distribution, and we will see that its application for this different field in the civil engineering in the subsequent using these properties. So some initial moments that we are discussing now will be mathematically what I have just shown you graphically can be checked here through this graphical through this mathematical expression. This is your expected value of this x, that is the mean is alpha by alpha plus beta. So depending on this parameter this is the value we will get as its mean. Similarly the variance can also be calculated. We know that this is the second moment with respect to the mean, it will come as this alpha beta divided by alpha plus beta plus 1 multiplied by alpha plus beta whole square. Now the this coefficient of skewness, you can see our previous lecture how to calculate this variance of x. It is the integration from over the entire support of any distribution x minus mu whole square multiplied by this density. It will give you the variance, and if you do it for this beta distribution, this will come to this form. Coming to this skewness again, you know, this is the third moment with respect to the mean, and when you are talking about the coefficient of skewness, it is normalized by the cube of the standard deviation, or 3/2 power of the variance. So that is normalized. This is also discussed in these previous lectures. So for this beta distribution, if we calculate the coefficient of skewness, then it will take the form with respect to the parameters like this. Now you see here, as this alpha and beta, remember that this alpha and beta both are greater than 0. So now depending on if the alpha is less, beta is more, then this skewness is positive. That is what we discuss. So and again just opposite, if the alpha is more, beta is less, then it will become negatively skewed, what we showed graphically just now. And again that if alpha and beta both are equal to 1, then we get the uniform distribution on the interval 0 to 1. Okay. So this is also we have shown graphically a minute before. Now if we just have some discussion on this beta distribution, that is any random variable that is having the finite maximum and minimum points, and then that can be modeled as a beta distribution. Uniform distribution is also having the finite maximum and minimum, however the density is uniform within these limits. Now for the beta, just controlling those parameters, you can have the different shape and size of the PDF, probability density function. The beta distribution can have positive as well as negative skewness. Uniform distribution is a special case of this beta distribution. Just we discuss the duration of a particular project. These are some example in the civil engineering. When we take up some project, there is some belief that the maximum how long this project can take, that generally is known from this from our earlier experience, and you know the minimum duration is always lower bound is 0. So this so total duration of a particular project is known, is lower limit and as well as the higher limit from the earlier experience. So this kind of, so if we now want to model this, what is the total duration of a particular project, can be modeled through this beta distribution. Then say another example can be the number of structures to be maintained from a group of structure. Say in a project we have constructed 10 such structure in a region, and we need to know that how many structures on an average needs to be repaired or take actually the budget in the maintenance. If we just want to know, then we have to know that how many structures is supposed to need the maintenance. So we know that its lower limit obviously 0, and its higher limit is the maximum number of structure that we are having. So having these two limits known and on the different properties of those structure, we can just model this kind of problem also through this beta distribution. We will see some of the application in the subsequent modules. Next we will discuss another distribution which is known as gamma distribution, and this gamma distribution is also very important, and just while discussing the bounds, we have seen that this gamma distribution is also similar to our previous lecture, exponential distribution, which one is also support is from starting from 0 to infinity. So it is having a lower bound 0. So this gamma distribution is also having the lower bound at 0. So generally, the random variables that is having a lower bound at 0, such as river flows, this kind of cases we can use this gamma distribution to model this kind of variables, and this can also be viewed as the waiting time until the beta-th event of a Poisson process. So we have discussed this Poisson process earlier, and there if we just wait for the so instead of the first failure, if we say that okay some nth or beta-th failure, then this taking that these events are mutually independent to each other, what we can assume that there are so each distribution is exponential. So we can say that this is a summation of the beta number of exponential distribution, and we can show that if we just sum it up, then this is approaching to a gamma distribution. So the gamma distribution forms looks like this, that fx x is equals to 1 by beta power alpha gamma alpha x power alpha minus 1 exponential minus x by beta, and support is, as we told, that is it is x is greater than 0 and both the parameters are also greater than 0, and for the otherwise it is 0 means that negative side this PDF is 0. And the gamma distribution that we discuss in the while discussing that beta distribution as well, that gamma alpha with this parameter alpha is defined as an integral from 0 to infinity x power alpha minus 1 e power minus x dx. So now we will see there are some easy way of this calculation. There are some simple rules how to get this gamma form, because this gamma is very important. This gamma function is very important for this this gamma distribution, both as well as for this beta distribution as well. Okay, so this is the form, that is gamma alpha is equals to alpha minus 1 factorial for the alpha equals to 1, 2, 3. So when the when this is an integer value, when this alpha is an integer value, then we can say that this value of this gamma function is equals to alpha minus 1. So just a simple example can be like this, that gamma 4 is equals to 3 multiplied by 2 multiplied by 1, which is equals to 6. Okay. So the second rule that tells that this gamma alpha plus 1, this gamma alpha plus 1 equals to alpha gamma alpha. This is for any value, not only for the integers, for any positive value this relation holds good. So if I just want to know that this gamma 4.5, then what we can write this one is that 3.55 gamma 3.5. Similarly, this gamma 3.5 can be written that 3.5 multiplied by 2.5, then gamma 2.5. In this way, you can go and get that 3.5 multiplied by 2.5 multiplied by 1.5 multiplied by 0.5 multiplied by gamma 0.5. Now, you cannot go further because that is the negative side. So ultimately, for any value, any positive number, you can take it reduced to some gamma function which is between 0 to 1. So if these values are known to us, then any gamma value can be calculated. So generally in the textbooks, these values are known, this 0 to 1 gamma values are known, and from there we can calculate this one. One special thing that is there, that is that gamma half, this gamma 0.5 is square root pi. So this gamma 0.5 is equals to square root pi, this is known, and other values can be obtained through this numerical integration. This is not a closed form integration. This can be obtained from the numerical integration from 0 to infinity t power alpha minus 1 exponential minus t dt, and this is generally available from some standard probability table as well. So we can calculate the any value that we need for this gamma function, and this gamma function is useful for both for this gamma distribution as well as for the beta distribution. Now we will see the cumulative distribution of this gamma distribution function, which is, you know, again given by, this is the normalizing factor is taken out from 0 to x, that is the left support to a specific value x of this integration, where again this gamma function is equals to 0 to infinity x power alpha minus 1 e power minus x dx. Now if we see one PDF of this gamma distribution, you can see that it's ranging from 0 to infinity for a specific parameter set. Here is alpha is equals to 2 and beta equals to 2, and you can see this is a positively skewed distribution, and basically this gamma distribution is always positively skewed, and its lower bound is 0. Okay. So, this alpha beta parameters are also shown here, alpha equals to 2 and beta equals to 2. The distribution looks like this, just for a standard example of this, how this density function for this gamma is looked like. And for the same parameter set, alpha equals to 2 and beta equals to 2, this is the CDF cumulative distribution function for gamma distribution looks like this. So, it starts from 0 obviously going to the total probability 1, and it is from support is 0 to infinity. So, this one is asymptotic to 1 at infinity. Now, we will discuss about the effect of change in the parameter values on gamma distribution. The two parameter, these two parameters are, one is the scale parameter alpha and another one is the shape parameter beta. This gamma distribution is a positively skewed distribution, which we show in the PDF plot of the PDF for a particular set of parameter. So, this is always positively skewed. Now, for a fixed value of beta, if we freeze this beta and if we increase this alpha, then this skewness increases, sorry, this skewness decreases. So, for a fixed value of beta, the skewness decreases as alpha increases, and for a fixed value of alpha, the peak decreases as beta increases. So, this thing we will just show in pictorially as well, how it is changing and how these two parameter can control to basically to capture a wide range of distribution, that we will see. And one more thing, one more very special thing here is that this exponential distribution that we discussed in the last class is a special case of this gamma distribution. When we put this alpha equals to 1, basically we get this distribution, as this gamma distribution will be equal to this exponential distribution. This we can check once here, that this is a form. So, if we just put that alpha is equals to 1, so 1 by, so this will become 1 by beta, and we know that gamma 1 is equals to 1. So, 1 by beta, and this x power 1 minus 1, so this will vanish, this will be 1. So, e power minus x by alpha. So, what we have seen in the exponential distribution might be we discussed that lambda e power lambda x. So, if we just put the lambda equals to 1 by beta here, so we are getting the same form of the distribution of this of the exponential distribution from this gamma distribution. Now, we will see the how this pictorially we can see that this effect of this alpha and beta. What we have discussed is that for a fixed value of beta, the skewness decreases as alpha increases, and for a fixed value of alpha, the peak decreases as beta increases. So, this is the first example. Here the this beta, all for all these three distributions, all are gamma distributions with the different values of alpha and beta, and for these three distributions this parameter beta is same, which is equals to 1. So, beta equals to 1 for all these three blue, black and green color PDFs. Now, for this blue one, this alpha value is 2, then for the black it is alpha is 4, for this green alpha is equals to 8. So, you can see that how the skewness. So, this is, you can see that all these are positively skewed. Now, the skewness is decreasing as the alpha is increasing. Similarly, if we keep that alpha to be same, that is here again three different plots are shown here, where the for all these distributions parameter alpha is equals to 2. For this blue, black and green, this alpha parameter is 2, and we are changing the beta. So, for this blue one beta is 2, for this black one beta is 3, and for the green one beta is 4. So, what we have seen that when we are increasing this beta, then the peak of this distribution is decreasing, which just we discuss. And now, if we just put this alpha is equals to 1 and this beta equals to 2, and we showed that if alpha is equals to 1 irrespective of whatever the value of this beta, then it is basically becoming an exponential distribution. So, now we can see here that this 1 by beta, so it is becoming 1 by beta e power minus x by beta, that fx from this gamma, if we put that alpha equals to 1. So, this support are same, x is greater than 0. Now, you see that when we discuss this exponential distribution, might be we have used the parameter alpha e power minus lambda e power minus lambda x, and we have shown that this when we are relating to its expected value or this mean, or that we have seen that this lambda is related to this 1 by x bar. Okay. So, here that, so this beta is here is shown that if it is that 2. So, here the example that we have shown, this beta what we are using as 2. So, its mean is becoming that, so it is half e power minus half x. So, its mean value we know that it, so not the mean one, at the x equals to 0 the values is 1 by 2. So, here also in this plot you can see that at x equals to 0 the value of this, so it is starting from exactly from 0.5. So, if we change this beta accordingly, maybe the starting point of this density will change, but the shape will be same as that exponential distribution as long as the alpha is equals to 1. For this gamma distribution, these are some initial moments, that is the expected value of this alpha is of this x is equals to alpha multiplied by beta. The variance is given by alpha beta square, and the coefficient of skewness is given by 2 by a square root alpha. So, here you can see that coefficient of skewness is depending only on one parameter, which is alpha, and as this alpha is greater than 0 and this skewness always we are getting the positive one, and this one is if the alpha increases, this skewness decreases. Now, some example of this gamma distribution, where the possible application of this gamma distribution to the civil engineering problems. Suppose that there are, so basically before I come to this specific example, that when we started this gamma distribution, we told that anything that is having some distribution like that exponential distribution, or in the discrete case we have discussed that Poisson distribution. So, now if we just add up those distributions, and the resulting distribution will basically come to a gamma distribution. Now, in different application, if you can see that okay, this is the summation of this kind of the waiting time, or the first failure or the second failure, a system involves in different subsystem which is following the exponential distribution, can be add up to the can be add up, that add up in the sense that these are mutually, these events are mutually independent. Then what you can, then in those every cases you can think of this gamma distribution. Here one such example is given as is that example of the 2 pump system. So, in a system 2 different pumps are used. So, not only 2, it can be more than 2 as well, it will be just the summation. So, now, so these pumps are operating independently to each other. So, this independent, now we understand this, why we are using this independent is that we have to add up this one. Now, the occurrence of the breakdown of one pump is a Poisson distributed random variable. Now, the lifespan of each pump can be described by in terms of this exponential distribution, whereas the life of the total system. Now, when we are coming to this total system, it should be the sum of that those many pumps. So, it may be 2, 3 or whatever. So, which is the sum of, in this case is the 2 pumps. So, maybe model using through this gamma distribution. Okay, this is one example, and in particularly in the hydrological application, this river flows generally has been seen that can be very useful for this gamma distribution, in the sense that this gamma distribution, just by controlling this parameter, the wide shape can be captured shape. And one thing is that for this river flow, we know that this the minimum flow is 0. So, this is always bounded by 0 here. Now, that depending on this how the the pattern, how the characteristics of that flow, it can be a kind of a skewness can be, so very that peak can be of very low flow, the density, the most expected values can be low here, and just by adjusting this parameter the same gamma distribution can take that any form like this. Sometime what happens for these very large rivers, this flow is basically a symmetrical shape and having a kind of normal distribution, but obviously again there also the lower bound is 0. So just by adjusting these two parameters, this alpha and beta of this gamma distribution, you can control this shape starting from this exponential to this positively skewed even to the symmetric. So that is why this we found that the application of this river flow modeling is very suitable for this to use this gamma distribution. So that is why there is another application of this gamma distribution to this civil engineering problem. Next, a class of distribution which is known as Pearson distribution. The Pearson distribution was proposed by Karl Pearson to model the frequency distribution of skewed random variable. The general form of this distribution is given by this expression, which is f(x) exponential minus infinity to x. This form is t plus alpha beta naught plus beta 1 t plus beta 2 t square plus this is an infinite series and take this form. Now this form, just controlling this its parameter, there are 7 different types of distribution can be obtained from this Pearson distribution. Now in our civil engineering particularly we have seen this application in this hydrology and as well as other fields in civil engineering, which is important is this Pearson type 3 distribution. So this Pearson type 3 distribution is takes the form like this, which is a 3 parameter distribution. So this Pearson type 3 distribution is a 3 parameter distribution, and sometimes it is also called as a 3 parameter gamma distribution as well. The PDF of this distribution is given by f(x) p naught 1 plus x by alpha power alpha by delta exponential minus x by delta. Now this mode where this mode of this distribution is at x equals to 0, and this p naught is the value at x, value of this density at x equals to 0. The lower bound is at x equals to minus alpha, and the difference between the mean and mode is delta. Now if we just discuss its relation to this gamma distribution, then we can see that means particularly the question that why we call it as a 3 parameter gamma distribution. We have just now we have seen that this gamma distribution is a 2 parameter distribution. Here this delta is making the difference between these two cases that we are discussing, is the difference between the mean and the mode. Now this difference between the mean and mode, you know that this gamma distribution is positively skewed distribution, so this mean and mode are not same. So but for the gamma distribution, this mean and mode, the difference between this mean and mode are not specified. Now for this Pearson type 3 distribution, this mean and mode is having this is this delta, which is a parameter of this distribution. Now in the gamma distribution, again in the gamma distribution we have discussed that the lower bound is at 0. Now here we don't want to keep this lower bound at any specific point. So here this lower bound is also controlled by another parameter, which is minus alpha. So it is more general with respect to this gamma distribution, which is, but this its application to this civil engineering problem is mostly to the frequency distribution. There is another one is known as this called log Pearson type 3 distribution. For example, we have seen that normal distribution or Gaussian distribution, then in relation to that we have also seen the log normal distribution. So for this very high value, if we take the log, then we have seen that it is coming to this normal distribution. So that in that case we have used that, and we have discussed that log normal distribution. Similarly, for this Pearson distribution type 3, when we have seen that some extreme value, if we just take the log, then it is fitting to this Pearson distribution, then that original random variable is known as that it is supporting the distribution of this log Pearson type 3 distribution. So so that's why means we can make an just a correspondence between this normal log normal and Pearson log Pearson type distribution. So if a random variable y is equals to log x follow the Pearson type 3 distribution, remember that what we are talking about here is the y. If this y is related to some other random variable through this log, if this y follows that Pearson type 3 distribution, then this random variable x follows the log normal type 3 distribution. The log normal distribution is a special case of the log Pearson type 3 distribution that just now we told that just depending on how we are controlling the parameter of this Pearson distribution, when this random variable y log x is symmetric about the mean. So this is also controlled, this can also be controlled. So we know that for this log normal distribution, after taking the log, it's become symmetric. So when this y after taking this log of this x is symmetric about the mean, then that is a special case of this log Pearson type 3 distribution, which is a log normal distribution. Now examples of Pearson type 3 and log Pearson type 3 distribution in civil engineering. Sometimes this annual maximum flood peaks are generally described by Pearson type 3 distribution. If the observations present very highly positive skewed data, then the log Pearson type 3 distribution is used for modeling. This log transformation reduce the skewness and can even change a positively skewed data to a negatively skewed one. So these things, that is when we are talking about this maximum flood, this annual maximum flood. So in a year we have, from the data that we are having, we are just picking up the maximum values, and when we are modeling that only those peaks, only those maximum flows that is available to us, then it is observed that this Pearson type 3 distribution is very important for its, particularly for its frequency analysis, that is its return period, which is very important for example to design a reservoir dam or that kind of thing. So just I want to know that what should be the possible return period of the occurrence of this extreme flood. So to when we are modeling those extreme flood, then for a year, so that the annual maximum I have to pick up and model it through this probability theory, and it is very widely for in this cases this use of this Pearson type 3 distribution and log Pearson type 3 distribution for its frequency analysis is very wide. And we will see this application specific to this problem maybe in the subsequent module. Then another family of this distribution, again like that Pearson distribution we discussed just now, is the generalized extreme value distribution. So this generalized extreme value, when we are talking about in the context of this civil engineering, we are referring to both this maximum and minimum values. So not only for, so if we take that river flows, it is not only for the maximum flow, as well as we are talking about the minimum flows as well. So now we will see that using this extreme value distribution, how these three can be modeled. So this generalized extreme value distribution are a family of continuous probability distribution that are used to model the maximum and minimum limits of a normalized set of independent and identically distributed random variables. These distributions are asymptotic and depend on the nature of the tail of the distribution of the basic random variable. Now this, when we are talking about this tail, maybe this is the word that first time we are using in this course. What we are talking about, the tail is the towards the extreme end of a particular distribution. So we just, for example, that just now what we discussed about this gamma distribution, what we are talking about tail is that this one, where this particularly this kind of area where this in the respect of this blue, generally the available data is also less, and we need some special care at this zone. So this is known as the tail of any distribution. So when we are talking about this extreme value distribution, so these distributions are asymptotic depending on the nature of the tail of the distribution of the basic random variable. Now this is the generalized extreme value PDF. This looks like this, which is a looks a mathematically complex form, but if we just take that parameters in a group wise, then it is not that that difficult to tackle here. What we are talking about, that here this xi x minus mu by sigma, this group of parameter here, there is a xi is one parameter, then this mu and sigma, this combination should be greater than 0. So that is basically the support of this distribution, and this mu is the location parameter, and this sigma is the scale parameter, and xi is the shape parameter of this distribution. Now as we are having these three parameters, just by controlling them, satisfying this condition, of course, then we can arrive at different distributions. So the cumulative distribution of this one, of this general form, first of all we are talking about, is we will come to this one, this exponential to this group power 1 by xi. Now this, based on the tail behavior of the distribution of the basic random variable, there can be three types of the extreme value distribution. The type 1, it refers to the Gumbel distribution, we will see in a minute. The type 2, it refers to the French distribution. Type 3, it's referred to the reverse Weibull distribution. We will discuss the Weibull distribution and we will see that how it is related to this extreme value distribution is related to the reverse Weibull distribution. Maybe this distribution, this Weibull distribution will be covered in the next lecture. So before that, we will just see its effect of this different parameters of this, how this PDF looks like. So here this mu, the blue one is for the mu equals to 1, sigma equals to 2. This green one is the mu equals to 1 and sigma equals to 1, and this red one mu equals to 2 and sigma equals to 2, and their CDF looks like this with the same set of parameter, this blue, this green and this red. So how this is, means it basically it depends on this, how this one means how distributed on this entire range of this random variable. Yeah, this should be capital F. So one correction here, this should be capital F, because you know that by this time that CDF, the notation that we are following is this capital Fx. The other distribution is the Weibull distribution. Maybe we will discuss this distribution in the next lecture, and there are other distributions as well, which are the chi-square distribution. While this at the starting of this lecture we just shown that this chi-square distribution, F distribution and T distribution, these are the statistical, these are very useful for the statistical test, and also the Weibull distribution that we are discussing, maybe it is pending for this class, maybe we will discuss in the next lecture. So we will continue one more lecture in this module to complete that, whatever the standard probability densities and their different properties and their possible application to this different civil engineering problem we will see, and these properties will be used to model the different problems in civil engineering in the subsequent module. So so far, thank you.